Okay, so good afternoon. So today we'll continue on the implementation of synchronization objects. We'll continue where we left off last time, which is basically how do we implement semaphores. Now, if you remember, semaphores have two functions, the P functions and the P function and the V function. P is going to decrement, and if the value of the semaphore is less than, it is not positive, if it is not more than 0, then it's going to wait. So the way we're going to implement this is like our previous implementations. We're going to have this time the semaphore spin lock for our semaphore, which we're going to use to create mutual or ensure mutual exclusion whenever we want to change the internal state of our semaphore. In this case, the internal state of the semaphore is basically the queue of waiting tasks and also the value of the semaphore. So if the value is 0, then we'll just put this TCB into the waiting, and we call this suspend. If the value is not 0, meaning that if it is positive, then we just decrement the value and unlock the semaphore. In V, we again use the spin lock.lock and unlock at the beginning of and the end. Then we check. So when we call V, we check if there are any waiting threads. If there are, we remove them and we make them ready. And if there are none, then we increment the value. So one thing I want to emphasize, the only thing here is that P is supposed to decrement the value and V is supposed to increment the value. And that's the functionality of P and V. So this is how we defined P and V. Now, if you look at this implementation, you see here that in this if, the value is not incremented, and in this if, the value is not decremented. So I'm incrementing value only in this else and decrementing the value only in this X. The reason for this is just implementation. So functionality is different from implementation. Now, in our implementation, what is happening is this, we could actually do this. We can do value plus plus here, and then value minus minus here. But then we're just canceling them out because what's the point of incrementing and then coming here and decrementing, right? Because if there is somebody waiting, we want that somebody to start running. So instead of duplicating the work of incrementing here and decrementing here, we just factor it out. It's very similar to our implementation of the internal value of mutex, for example, where if somebody is unlocking and somebody is waiting, we really don't change the value of the mutex. We leave it as is. So just to show you, if you go back to the implementation of mutex, you can see a similar approach. So if you look here, I'm changing the value to free and busy only inside these else's. And I don't make the value free here and I don't make the value busy here, because what's the point? This guy can do value equals free and then somebody else comes here, wakes up, and does the value equals busy. So we just factor this out. We say, what's the point of duplicating the work, right? So that's something to note. So it's the very similar concept is being used. Now, okay, so keep going. So now the question is, can interrupt handler use P or V? Now the answer is interrupt handler should not use P, definitely, because P has this suspend here. So we don't want the interrupt handler to be suspended because interrupt handler is really not a task, and we don't want it to be treated as a task. But it definitely can use V, because in V, you're just sending a signal to whomever is waiting, right? So V is okay to be used, but P is not really okay to be used by interrupt handler. Okay, now I know how much time you guys have put in ECE 252 to study semaphores. But at the end of the day, this is a text out of Dijkstra's own paper, and Dijkstra is the one who actually invented semaphores. And he says that we have a problem with semaphores, and the problem is that they're dual purpose, meaning that they're used for two different purposes. The first purpose is mutual exclusion. So you can use semaphores to have mutual exclusion. So if you have a semaphore that you initiate to 1, so if you have a binary semaphore, you can use that as a tool to ensure mutual exclusion. But you could also use it to for scheduling constraints. And what do I mean by scheduling constraints? I'm referring to wait and signal, portion of the semaphores. For example, if you are to implement a bounded buffer, if you probably remember this from ECE 252, when you have producer and consumer, and let's say you want the producer to wait if there are items, if there are no empty slots in your bounded buffer, or if you want the consumer to wait if the bounded buffer is empty, you still can use actually semaphores to wait and signal. So for those of you who have forgotten, go and look at your ECE 252 notes, or if you want, I have covered this in SE 350. So the link to SE 350 is on my website. So if you want, you can just go there and look at the synchronization slides or the videos to refresh your memory. But anyhow, so this dual purpose makes semaphores complex. So this complexity is in reading the code. So when you read a code, you really don't know if this semaphore is used for mutual exclusion, or if this mutex is, or if this semaphore is used for wait and signal. When reading your code is hard, then understanding it is also hard. And when the understanding is hard, then debugging becomes hard as well. So all in all, using semaphores is going to make your coding experience difficult. So the recommendation is to avoid semaphores as much as you can, and don't use them in your code for synchronization. Now, the alternative to semaphores is monitors. And if I'm not mistaken, you probably didn't spend that much time on condition variables and monitors. So in the during the tutorial session previous week, last week, I basically covered on Friday. I covered condition variables and monitors, and I ran through an example of a reader and writer lock. So definitely go and watch that tutorial to refresh your memory about condition variables. And also, over there I did some analysis of the code, which you will need to know for the future quizzes. So I'm gonna just move over these because I covered them during the tutorial. So I basically just jump to an example of using condition variables to implement bounded buffers. And so you probably remember this bounded buffer example. There is this buffer that we don't want it to have more than a max items on. Now, there are producers who produce items and there are consumers who consume items. And as I said, we want producers to wait if there are no empty spots left, and we want consumers to wait if there are no items to be consumed. Now, to implement this with monitors, we need a mutex for mutual exclusion. So every time we want to change the state of the buffer or check the size of the buffer or any access to the buffer, we need to lock this mutex. So the buffer is basically our shared variable that we want mutual exclusion on. And for that, we will use this BB mutex. Now, for the waiting constraints, so this is mutual exclusion. The condition variables are used for scheduling. And again, don't mix up scheduling with operating system scheduling. Here, scheduling, I mean scheduling constraints or conditions that you want to have in your code. So I'm talking about programming, meaning those waitings, right? If you want the consumers to wait or if you want the producers to wait. So some order of execution you want to have, you use condition variables for those. Now let's look at the code for the producer. At the beginning and the end, we are going to lock the mutex to have mutual exclusion. Then in a while, so this one is very important. I guess, I mean, I just looked over your lecture notes from ECE 252, and I think there you were told to use if. We'll see that if is not appropriate. If is only valid in a certain implementation of condition variables, but we'll cover that. But generally speaking, we use a while to check for the condition to be true. So in this case, the producer wants the buffer not to be full. If it is full, then in a while loop, we're going to call wait. We're going to wait for consumers, and if there are the space here, then we just put our item. We enqueue our item in the buffer, and we unlock the mutex. So here I have a mistake. So this should be just BB mutex dot lock and BB mutex dot unlock. So again, at the beginning and end, we lock the mutex. We check for the condition here in consumer. We want the buffer not to be empty. And if it is empty, we'll wait. Then we consume an item, and then we signal producers. So when producers produce an item, they signal consumers. When consumers consume an item, they signal producers. Now, let's talk about that if versus while. So again, why are we using while? Now, should we use while or should we use if? In practice, if you're going to use, a mainstream libraries like pthreads, like Java, then use while. But there is a single implementation of monitors called Hoare style monitors. For those, it's okay to use if. Now, let's see the difference between Hoare and Mesa. So these are two different scheduling, choosing between while and if. So with Hoare monitors, what happens is when a signal is called, when you call signal on your condition variable, the mutex and CPU will be given to the thread that receives the signal. What do we mean by this? We just mean that we immediately, after a signal, context switch to the thread that receives the signal. So, and we transfer the mutex. So remember that the one who is sending a signal has locked the mutex. Now we grab the mutex from this guy and give it to this guy, and we start running this guy immediately. Now in this case, when this happens, then you really don't need to check again, because whatever event you were waiting for has happened, and atomically we have context switched to you. So you don't need to check it again. So then you go ahead, you don't need to do anything else. And once you unlock the mutex, once you're done with your critical section, then we're going to context switch back to the signaler, the one who sent you a signal, and continue there. So this implementation is called Hoare style monitors. Now, compare that with Mesa monitors. In Mesa monitors, when a thread calls signal, all that we do is we change the state of the waiting thread to ready. So that's all we do. We do not context switch immediately. We do not transfer mutex. We just make that thread ready, and that's it. Now it's up to the operating system's scheduler to pick the next thread to run. And it well could be that we run ourselves and finish. And once we're done, at some point, the scheduler picks the thread that just woke up and executes that thread. So this one is called Mesa. Now let's compare Mesa and Hoare. So Mesa is a lot easier to implement. If you want to implement monitors, if you're writing a library, like let's say if you're writing pthreads and you want to implement monitors, it's much easier for you to implement Mesa. Because with Hoare monitor, you have to do a lot of stuff atomically, and that makes the implementation a lot harder compared to Mesa. That's why almost no, I don't know any library that implements Hoare monitors. So if you find any library that implements Hoare monitors, let me know, because I don't think there are any. Usually Hoare monitors are there just for, teaching and textbooks. The theory of it is interesting. Analyzing it is easier, right? But implementing it is really hard. That's why nobody implements Hoare monitors. So the chances are that you will never use any library that uses Hoare style monitors. Therefore, every time you are using condition variables, make sure that you have a while here and not if. Now let's see why. So let's look at the example we just implemented with monitors. In particular, let's look at the consumer producer example. So this is the code. If you remember, these were while. Now I changed them to if. So instead of having while, let's put if, and let's see what happens. With Mesa implementation, let's see why this is a bad choice. So let's run the example. So this is our buffer. Initially, it's empty. This is our monitor. We have the mutex. We have the empty CV. There is a full CV as well, full condition variable, but I'm not going to use it in this example, so I just dropped it from this. And then I have the CPU state. So somebody is running at any given time, and then I have the ready queue, the tasks that are ready to be executed. Now, let's assume that initially your queue is empty. Basically, this is your bounded buffer. The bounded buffer is empty. And let's say T1 is running, and let's say T1 is a consumer. Oh, somebody is asking how hard is it for monitors? I don't understand the question. Can you elaborate what you mean? Okay, so now let's look at T1. It tries to lock the mutex. Nobody is contending, so the monitor is locked by T1. Then it checks for the queue. The queue unfortunately is empty, so it cannot consume. So it will wait. Now I have added T1 to the list of waiting threads on empty CV, and I have unlocked the mutex. So the mutex is unlocked, right? So this should happen atomically. We unlock the mutex and put T1 to sleep. So now T1 is on the waiting list on empty CV. The mutex is unlocked. Nobody is running. Ready queue is null. Queue is empty. Let's say at this point, T2 comes in, and T2 is a producer. Now, T2 is running. T2 checks the mutex. The mutex is unlocked, so it locks it. Then it looks at the queue. The queue has a space, so it can produce an item. So it adds the item to the queue. So queue.add the item. So now we have an item. Now, at this point, T2 is going to send a signal to empty CV. And by this signal, we're going to put T1 to ready queue, right? So we remove T1 from empty CV and we put it on the ready queue. Now, let's say at this point, after we call signal, let's say T3 comes in. So now T3 has come. T3 is a new thread and it's going to be a consumer. Now, T3 goes to ready queue as well. So it's a new thread and it's going to be ready to be executed. Now let's look at the state. T2 has produced an item. So there is one item on our bounded buffer. The mutex is still locked by T2. Nobody is waiting. No consumer is waiting on empty CV. T2 is still running. And now I have two threads waiting on the ready queue. They're waiting for the scheduler to schedule them. Now, at this point, let's say T2 terminates. So T2 is done. Now a scheduler has to choose between T1 and T2. So the scheduler, let's say, picks T3 out of lock or lack of lock for T1. T3 starts running. Now T3 is going to lock the mutex. So mutex is locked by T3. Now T3 is going to check the bounded buffer, and the bounded buffer is not empty because there is one item that T2 produced. So T3 is not going to wait because the queue is not empty. So this means that T3 consumes the item that was put by T2. And don't forget that this item, when we put it, we send a signal to T1. So we were supposed to let T1 consume this item, but there is no guarantee. As we said, the signal just wakes you up. It doesn't schedule you right away. And this is what you're seeing here. So T1 became ready, but didn't run. Now T3 came, and the scheduler, for whatever reason, chose T3. Now let's say T3 terminates. Now we're done. So again, Mutex is unlocked. Nobody's waiting. T1 is ready. Queue is empty. Now a scheduler picks T1. So T1 wakes up inside wait, and it locks the Mutex. And what happens? Well, if we don't have a while here, and if we just have an if, we're not going to go back and check the condition. And we're going to just go to the next line. And this next line is going to remove an item from the queue. But unfortunately, the queue is empty. There is nothing in the queue. The item was consumed by T3. And this is error, right? So we're going to get an error. This would have been avoided if instead of if, I had a while. So instead of just checking once, if I had checked twice, or in a while loop, I would have avoided this condition, and T1 would have now again put itself to waiting. Now, if you want to ask, okay, what's the way to ensure that T1 gets to run instead of T3? That's a good question that you will see in the exam. So if you want, start thinking about that. So how can you actually have an implementation? So you definitely need to change this implementation to make sure that threads actually get to run their turn. So if T1 has come first, what's the way to make sure that T1 gets to execute first before T3? And I kind of, alluded to the solution in the tutorial. So at the end of the tutorial, for those of you who have watched it or were there, I talked about, readers and writers, and I said, how can we make sure that the writers get the lock or get to write in the order that they come to the system? And then we saw the solution, how we can ensure that. And to just remind you, the solution was to, instead of having a single condition variable, to make each writer have its own condition variable. So the same here. If you want, if you want the consumers to have an order, let's say first come first serve, then you will have to have each consumer have its own condition variable, and then you have to have a queue for all of these guys to put them in a queue. So you will have to implement that yourself. Usually the system libraries that you're using for condition variables, they don't guarantee any sort of first come first serve or anything. So you will have to implement it yourself manually. Okay, so let's move on. Now, another reason for you to use while instead of if is what you can see here from Java user manual. So in Java user manual, it shamelessly states that you might actually wake up for no reason, even without getting a signal. So it's possible that a thread calling wait wakes up without even receiving a signal. And that's why you definitely want to call while. So you want to check the condition again and see if really you're fine to go. And if not, then you want to put yourself to sleep again. So, okay, so somebody's asking if it is a while loop, what would happen since we are waiting on MTCV indefinitely in a while loop in T1? Yeah, as I said, this implementation could lead to a starvation for T1. So T1 could get starved. And again, I kind of discussed this during the tutorial. In another example, I talked about riders could starve precisely for this same reason. So a new rider comes and they get to go instead of the old riders. And I have a solution at the end of the slides. So if you're interested, go and look at the solution, how you can avoid this and how you can make sure that you avoid a starvation. So the same solution could be applied here to make sure that consumers don't starve. But it is a correct assessment of the situation, yes. So consumers could potentially get starved here. Good question. Okay. Now let's compare condition variables and semaphores. The main difference is condition variables are memoryless, as we discussed. So if you call wait on a, if you call signal in condition variables and nobody is waiting, then that signal is wasted. Whereas if you call V on a semaphore, you're going to increase the value of that semaphore. So it's kind of like it's going to be memorizing how many times V has been called. Whereas in condition variables, we're going to forget how many times signal has been called if there are nobody waiting. Now, generally speaking, here is the point that I'm going to tell you to kind of never use semaphores, right? So as long as you're not going to implement, you know, probably interrupt handlers or drivers, you should be able to just stick to monitors and without any problems. There are certain corner cases where semaphores might be preferred to monitors. One example is, let's say, in interrupt handlers. So this is like probably the second time we're talking about interrupt handlers. So let's say that there is this shared data that is shared between your kernel threads and your device driver. For example, let's say, again, I'm just making it up. Let's say you have an SSH daemon that wants to read incoming packets. I'm just making it up, right? So don't put much emphasis on this example, but for an example. And then you have your NIC that writes in a certain memory the packets that it receives. Now, this memory region is shared between this kernel thread or daemon and your device. So, for example, you want the SSH to just wait if there is no data, right? So maybe this kernel thread calls wait, checks the data, there is no data, it waits. Now you want to sort of wake it up when there is data. So let's say a packet arrives and you DMA it to that memory, and now you want to wake up your thread that was waiting for it. Now the interrupt handler, so once the data is there, if you remember, the device is going to raise an interrupt, and then interrupt handler, the bottom half, is going to wake up. Now you want the interrupt handler to notify this SSH daemon that data that you were waiting has arrived. Now, how do we do that? So if the SSH, for example, task has called wait on a condition variable, can we use normal condition variables in our interrupt handler to send a signal? Now, the answer is yes, but you have to be careful that you should not lock the mutex inside your interrupt handler. So if you remember, what I said was, if you want to use signal, wait, and broadcast, always lock the mutex first and then call these guys. Now, interrupt handler cannot lock the mutex because we talked about the fact that interrupt handler is not a thread and it cannot be scheduled. It cannot be suspended. So it should not use the mutex. It should not do mutex.lock. So that's off table. We can make it just do something that is called naked notify. And naked notify means that the interrupt handler calls the condition variable .signal without locking the mutex. So this is a naked signal. And it's possible there are corner cases that this signal could get wasted. And that's why it's not preferred to use condition variables in these situations. So this is one situation that it's better to use semaphores instead of condition variables, because there could be a scenario where the SSH thread, right before it is put to sleep, the data comes and interrupt handler is enabled, and then the interrupt handler sends a signal, and that signal gets wasted because the SSH thread has not yet called wait, or the wait has not yet finished. So because of these cases, and that's precisely why you have this naked notify, which is not perfect. It might be a good idea here to, instead of using monitors, use semaphores. So you could easily, instead of signal, call V, and instead of wait, you can call P in your semaphore, and that would be fine. So unless you're gonna do some sort of device drivers or interrupt handling coding, you probably will never have to use semaphores. So try to avoid semaphores as much as possible. As I said, the inventor of semaphores has pointed out that semaphores are just too complex to be useful, and we have alternatives. So the alternative being the monitors. Okay, now with all of that, let's look at the implementation of condition variables. So this is my class CV condition variables. It has a single private element, and that's the waiting queue that we're going to put queues to. We're going to put the threads to waiting. It has three functions: wait, signal, and broadcast. So let's look at wait. It's going to first add the TCB to waiting, then call a scheduler suspend, which then would release the mutex. And then it's going to, right after it wakes up, it's going to lock the mutex again. So here a scheduler will unlock the mutex and put this thread to sleep. When you wake up, the first thing you do, you lock the mutex again. So this is the implementation of that functionality that we talked about, right? So this is how we implement it. So inside wait, we put ourselves to the waiting, we go to sleep, and the moment we wake up, we try to lock the mutex again. Now let's look at signal. The signal is going to check the waiting list. If there are any, then we just change their state from waiting to ready, and we remove them from waiting. As you can see, we're just we're changing their state. They're making them ready. We're making them ready, right? We're not going to run them. And then finally broadcast. So we check the waiting list, and as long as it's not empty, so we make them ready. So this one is a while. So this wakes up everybody. This wakes up only one person. Somebody is asking, if he doesn't like semaphores, why invent it in the first place? That's a very good point. So usually you invent something and then you analyze it. So yeah. Okay. Okay, so that's that. Now let's ask a question. Why, like all the implementations so far that we've seen for semaphores, for mutexes, we had a spin lock of some sort in our class. So the class, mutex class had a spin lock. The semaphore class had a spin lock. Why don't we need a spin lock in CV? And the answer for that is that we actually are not going to use CV functions. So signal, broadcast, and wait, we're not going to call them unless we have locked a mutex. So this ensures mutual exclusion has been provided by the mutex, right? So that's why I told you that you always have to lock the mutex when you call wait, signal, and broadcast, because their implementation assume that these functions are going to be called inside your critical section. So the mutual exclusion is assumed in the implementation. Therefore, the programmer that wants to use these, they have to ensure that they have locked the mutex. So they're inside their critical section when they call these functions. Okay, now I have actually, I'm gonna just yeah, probably I'm gonna move on from these. So I have, so in these slides, I have tried to use semaphores to implement condition variables. Maybe I go over them really fast. You know, we know that semaphores are as powerful as locks. So let's try to use them to implement condition variables, right? One implementation that you might think of is for signal, just use V, and for wait, we kind of use P. So we unlock, we call P, and then we lock. So does this work? The answer is no. The reason this doesn't work is because we're using this semaphore, it's going to have memory. And this is against what we said, that condition variables don't have memory. So in this implementation, this condition variable will have memory. So if you call 10 times signal, then 10 waits are going to go to not have to wait. Whereas in you know, the definition of condition variables says that if nobody is waiting, then the signal should get lost. So take two says, OK, what if I can check? So instead of just calling semaphore, I check if there is anybody waiting. Then I call V. And if nobody's waiting, I don't call anything. Now, this implementation has a problem. And that problem is that I don't have any operation to access the internal value of a semaphore. I can't read the semaphore's value. The only two operations I have on the semaphore are P and V, and that's it. So I can't possibly do this. The other reason for this is that in this implementation, if we assume that, okay, this is fine, let's say we give it to you that you can check the internal of semaphores, this is not atomic. So the lock is released, and then P is going to be called to put things to sleep. And if you remember, I said that this has to be implemented atomically, but this implementation doesn't have it atomically. It was atomic in this one. So in our implementation, this is atomic. So as you can see, the scheduler is going to suspend and release the mutex at the same time. So this ensures atomic release of mutex and going to sleep. But this one here doesn't, because we first release and then call P, and we could indeed get interrupted in between, and that's something that we want to avoid. We don't want to get interrupted in between releasing the lock and going to sleep. So this implementation, for these two reasons, is not acceptable. So the third implementation, the idea here is to have a separate semaphore for each waiting thread, right? So every time a thread calls wait, we create a semaphore for that waiting thread. We have a queue of waiting threads. Then we unlock and put this in the and then call the P on the semaphore. And in our signal, we just check the number of semaphores that we have in this queue. And if there are any, then we unlock and then we call B. So with that, we're done with the implementation of multi-threaded kernels. What did we see in this? So we started by looking at how we can implement threads, how we can create threads, how we can context switch between threads. Then we switched gears and talked about synchronization. We talked about how we can use interrupts, disabling and enabling interrupts to ensure mutual exclusion, how we can then use atomic read, modify, store operations to implement spin locks, and then finally how we can use a spin locks to implement mutexes, semaphores, and condition variables. So by the end of this lecture, you should have a good idea of what it takes for a general purpose kernel to support multi-threading, both for kernel threads, so internal kernel threads, and also for user threads through system calls. So that's pretty much it with with multi-threaded kernels. Now our next stop is scheduling. So we're going to move on to scheduling. So we start with Uni Processor Scheduling, and then we move on to multiprocessor scheduling. Okay, so without any waste of time, let's start Uni Processor Scheduling. So what are we going to see? So we're going to see a little bit of history, a little bit of definitions, and then we start seeing a few famous scheduling policies. Okay, brief history of scheduling. So around 2000, the problem of scheduling in operating systems was kind of considered solved problem. So it was kind of like, okay, we're done. It was mature enough for the inventor of Linux to put a statement like this that, if I were to read this, and You have to realize that there are not very many things that have aged as well as the scheduler, which is just another proof that scheduling is easy. So this is like around 2001, scheduling was considered as a solved problem, an easy problem, something that we're done with, and we're gonna just be happy with it. Then came the end of Dinard scaling, if you remember from the introduction. So this is where we started having multiprocessors. So if you remember, before this, usually our systems had only a single processing unit. So there was a single CPU, and for that, we have solved the scheduling problem. Then came the end of Dinard scaling. We started seeing multiprocessors. And at this time, I have a quote from Linus that I will show you when we talk about multiprocessor scheduling. But around this time, he put in a statement saying that, so here he said that, oh my God, like scheduling is just done. We're done implementing it. When we started having multiple CPUs, he said that, sure, it's a little bit now not that easy, but it's still straightforward. So we can still do it. It's no big deal. We can still use what we've learned with Uni Processor Scheduling and apply it to multiprocessors, and we should be fine. Now, came 2016. So there's a paper that I have posted on the website. So if you go to the website, I genuinely invite you to read this paper. So this paper, I put it on in multiprocessor scheduling. So I'm talking about this one, this paper from EuroSys 2016. So the name of the paper is The Linux Scheduler, A Decade of Wasted Cores. Now, in this paper, the authors showed that the Linux kernel scheduler was as buggy as it could get. They showed that for some workloads, a scheduler was causing over 138x a slowdown. 138x a slowdown as a result of the way that the Linux scheduler was implemented. So this proved Linus to be wrong. So, multiprocessors brought new challenges to scheduling. And one could argue that it's still not a solved problem, not a mature problem for us to say, okay, it's done. But what happens was, if you remember, at the end of Dinard scaling around 2003-4, we started having multiple cores. But then around 2020-ish or 2019, so, starting from 19-something to 2004, we were just having single CPU. Now, from 2004 until 19, not only we have multiple CPUs, now we have other processing units in our systems as well. So it's not just CPU that is a processing unit. Your GPU is also a processing unit. Your GPU is probably running a lot of machine learning stuff, or it's capable of running. And it's not just that. With high probability, if you are, if you have a server in a data center, the NIC, the network card, probably has CPUs running the network stack. And probably your SSD has its own processing unit, and probably your FPGA has its own processing units. So now we are at the point in time where it's really challenging to a schedule. So it's not only not solved and it's not only not mature. There is, I think, a lot of work to be done when it comes to unifying and solving the scheduling problem in modern heterogeneous systems. I try my best to touch upon some of these new stuff at the end of this lecture, but probably I won't be able to, dive deep. This is an area that I'm actually interested in. I do some research. So those of you who are interested in doing, research in operating systems or systems in general, like distributed systems, reach out to me, if you want to do a project or you want to do a URA or something. So this is an area that I'm actually interested in. Okay, so let's make some definitions. So first, tasks, threads, and processes. When we're talking about a scheduling, we're going to look at it as kind of like a mathematical problem. So we're going to abstract away some of the stuff that we have talked about. So at this point, I'm not going to care about if I'm scheduling threads or if I'm scheduling processes or if I'm scheduling tasks in a real-time system, right? So whatever unit of work your system has, I'm going to take that as a unit of work, and I'm going to just talk about the mathematical problem of scheduling, right? So I'm going to use these words, task, threads, processes, interchangeably. And by that, I just mean that whatever that can be scheduled. Now, the term workload will be used to indicate a set of tasks. So a set of tasks, we call it a workload. And a scheduling algorithm is the algorithm that decides which task or thread or process to run next. The overhead of a scheduling is amount of work that your scheduler does to determine the next task to execute. So this is a time that your scheduler code is going to run on CPU instead of the tasks that it wants to schedule. So basically, you're using CPU resources for your scheduler, and this is overhead, right? If you remember, we want the operating system to use resources as less as possible. So any time that your scheduler is going to run on the CPU is going to be considered as overhead. How much time do I have left? About 20 minutes. That's good. Okay. Preemptive scheduling is a scheduling where the scheduler is able to preempt the running task. And non-preemptive scheduling means that if a task starts running, then the scheduler cannot preempt it. It has to run until it voluntarily gives up the CPU, either calls yield or maybe finishes calls exit or does IO or something, right? So basically the scheduler is not going to go and take the CPU away. So the task is going to have it until it wants it to. Now, the other category that we can think of is work conserving versus non-work conserving schedulers. So a work conserving scheduler is a scheduler that schedules a task right after CPU gets idle. So it doesn't leave the CPU idle at all. So if there are tasks to be run and there is a CPU idle, then schedule a task. So in these schedulers, you get the highest utilization because your CPU is always doing work, right? You're never going to leave your CPU idle. In non-conserving schedulers, you might want to keep the CPU idle for some reason. So you might actually think that, what the heck, why would anybody want to keep the CPU idle if you have tasks to run? And the answer is, here is just an example where it might make sense to keep your CPU idle even though you have work to do. Let's assume that in your system, it's a non-preemptive system. So if a task starts, it has to run until completion. Now, if you have priorities for your tasks, so you have a bunch of your tasks are low priority and a bunch of your tasks are high priority. Let's say you have a bunch of low priority tasks, and let's say these tasks are long. Let's say each one of them is taking like an hour. And let's say you have these high priority tasks that come very infrequently, and they're very short. Now, when your CPU becomes idle, if you have a bunch of low priority tasks and you schedule them, there is a possibility that a high priority task comes in that is very short and maybe has a deadline, and you won't be able to run it because you have already started a low priority task. So maybe I'm just making an example. I'm not suggesting what to do in certain situations. It differs case by case. But it might be a good idea to maybe wait a little bit to see if a high priority task comes in. And if you wait enough and it doesn't, then you can probably execute one of those low priorities. So again, this is an example. So in certain cases, it might make sense to have a non-work conserving scheduler, especially in real-time systems that do not support preemption. Okay. Now, for the rest of the slides that we will see, we're going to assume that we have preemption, and we're assuming that the scheduler is work conserving. So we're not going to focus on non-preemptive and non-work conserving schedulers. That is not what the lecture is going to cover. So as a disclaimer, so we're going to just focus on preemptive and work scheduling schedulers. Okay. So just a recall from, I guess, I think it was the operating system concepts. So if you remember, the cycle was that we had a bunch of tasks waiting in the ready queue, and we want to schedule them on the CPU. So the title of this lecture is Uni Processor Scheduling. So we're going to assume that there is only one CPU here. So once we cover uniprocessor, I'll talk a little bit, not much, about multiprocessor scheduling. But really, the question is, how do we choose the next thread from this ready queue? Which thread should run next? So that's the question. And scheduling answers that question. So different scheduling policies pick different threads to run, depending on the policy that they implement. We're going to look at a specific model of execution. So we're going to look at our tasks, which have CPU burst, then IO burst, then CPU burst, then IO burst, then CPU burst, and then IO burst. So during this time, your thread is going to do some computation. Then at some point, it's going to get blocked for IO. So you're going to be doing IO. And then once the IO is done, you're ready. And when you get scheduled, you're going to have a CPU burst, meaning that you're going to have some instructions to execute until you call IO again, and then you call CPU, and then you call IO, and so on and so forth. So this is the model that we're going to look at. So this is our tasks are going to have these CPU bursts, IO bursts, CPU burst, IO burst, and again and again and again. If you look at a chart where on the x-axis you have the burst duration, how long it takes for each CPU burst, and how many of these bursts had that particular duration, then you usually get something like this. So this is the graph that you get. And this basically means that most of your CPU bursts are short, and you probably have a few long CPU bursts. So this is where we're going to focus. We're going to focus on situations where most of our CPU bursts are short, and we want to have a test case. We want to have an algorithm that handles this well. Okay, I got a question. So with a scenario where we want some idle time, be a situation where we have tight thermal constraints, i.e., we use idle CPU as a method to reduce CPU temperature before starting another task, essentially giving the CPU time to cool down. Just curious. Thanks. That's a good question. So this actually happens, right? Most of our systems have this, that you really want to let your system cool down. Now, most of the systems that I know, instead of really idling the CPU, they change the voltage and frequency of the CPU, right? So basically, they bring the voltage and frequency of your CPU really down. So they make your CPU to get really slow, and this allows the CPU to cool down. So the higher the voltage and frequency are, the hotter your CPU gets. So if you want it to cool down, you just bring the CPU and voltage and frequency down. In some cases, you might actually want to turn them off completely. When you turn them off, then they're basically out of service. So you shouldn't consider that as non-work conserving, because you basically turn them off, so they don't exist anymore. It's not like you have them and you're not scheduling on them. But generally speaking, yes, you might actually want to have some non-work conserving scheduling for your system, which gets hot, right? So for whatever reason, let's say you don't have a good thermal heat sink, and you want to use the scheduler to cool down your CPUs. That's possible. So yeah, that was a good question. So what does burst mean? So what I mean by burst, I mean bunch of instructions that there is no I/O in them, right? Let's say you are doing a matrix multiplication, you're doing like hundreds of multiplies on registers, so there is no I/O, or you go to memory and you come back, so you don't need any I/O, so you can just go without any interruption until sometime like you call I/O, and now it's you get you have to be suspended. So from when you get to run until you yourself call I/O to get suspended, this is a CPU burst. This means that you can, in this time, if you're given CPU, you can use it. So this is what we mean by a CPU burst. So you have instructions to run in a burst, and then you call I/O. You have to wait. Once you come back, you will have another CPU burst. You will have a bunch of instructions to execute until next time you call I/O to be suspended. Okay. So for now, we're going to assume that like we have one program per user. So let's say one, instead of program, I should have used process. So one process per user, one thread per process. So this is what we're going to assume, and we're going to assume processes are independent. These are not usually the case in all systems, right? So in many systems, users have multiple processes running. You have multiple threads per process, and then you have you might have dependency between your processes. Maybe they're they're synchronizing on a file, or there's a pipe between the processes. So we're not going to consider those. To just make everything easy, we're going to just focus on a simple setting where you have one thread per process, one process per user, and totally independent processes. Okay. Now, oh, somebody's asking about I/O burst. Yeah, so one thing that I probably won't have any time to cover is that operating systems actually do a lot of work for I/O. So it's not like, when you call I/O, when you want to read a file or write a file. If you remember, we talked about DMA, right? And DMA could be considered as a bunch of instructions being executed for the I/O to happen, right? Although you're not going to use the CPU for those, but you're going to use a DMA engine or something, right? So you also have I/O burst, right? Where you're doing I/O operations. In fact, the operating system has an I/O scheduler. So if you look at Linux, it has a CF, the Linux CPU scheduler is called Completely Fair Scheduler, CFS. And the iOS scheduler called Completely Fair Queuing, so CFQ. So there are two different schedulers. I'm not going to talk about iOS scheduling, but generally speaking, I/O is like when you call I/O, it's not just as simple like give me a file or read. Like it also has the steps to be taken, right? Setting up the DMA, reading, writing, handling the I/O requests and such. So yes, it is a burst, right? If you're doing a DMA, if you're reading 1 GB out of your SSD, right, it's going to take time and it's going to be in a bunch of instructions, although not executed probably on your CPU, but scheduled on your DMA engine, for example. The same with NIC, the same with GPU, and so on and so forth. So yes, you might have an I/O burst, similar to CPU burst. Okay, so let's continue. Now, the metric that we're going to focus on when we're talking about different scheduling policies, we have two metrics. The first one is usually average response time. What does response time mean? Response time means from when your task is submitted to the system, from when your thread becomes ready. Like let's say it's done with I/O, or it received the signal and now it's ready, until it finishes, right? So that's the response time. So every time you come back from suspension until you finish execution and you go for another I/O burst. So between your I/O bursts, and I have to say, like, consider any suspension as a different period for your task. So your task gets suspended until it gets ready. So this is a time that we don't care. But from ready until it gets suspended again, so this is a time that we care about. So this is your response time. So from when you're ready until you're done for another suspension. Now, it takes time for your suspension to finish, and then you become ready again. And then from ready to another suspension. This becomes your response time. So now, when I talk about average response time, I can look at average response time over a single task for each of its CPU bursts, or I can look at average response time over different tasks. So if I have 10 tasks in my system and each one of them has a response time of xi, then I can get average of those to be the average response time of my system. Now, average response time is not always what we care about. So for example, if you have a real-time system, you don't care about response time. You might care about deadlines. but this is for a later lecture. So we'll talk about that later. But for now, one of the metrics that we're interested in is average response time. The other metric that we're interested in is called throughput. Now, throughput means how many CPU bursts did you service in a specific time? How many tasks? Let's say if each task has one CPU burst and then they die, they terminate. Then throughput is how many tasks you executed during this time. If your tasks have a bunch of CPU bursts, then you can say how many CPU bursts you serviced in a given time period. So depending on how you define the unit of work, then you can say how many units of work finished in a specific time frame. And that gives you throughput. Now, one thing to note is minimizing response time and maximizing throughput are not necessarily related, right? So if you maximize throughput, it doesn't mean that you're going to minimize response time, or vice versa. If you minimize response time, it might not necessarily mean maximizing throughput. And examples of that will come later. So for now, just know that these are not necessarily related. So in particular, sometimes if you want to minimize response time, you might end up doing a lot of context switching. And if you do a lot of context switching, then you have a lot of overhead. So each context switching, you're gonna pay overhead, and this overhead is a time that you're using the CPU for extra work rather than running your threads. And this extra work is not going to be counted in throughput calculation. So in return, you're basically hurting throughput. And also, if you want to maximize throughput, you might want to minimize context switches. And if you want to minimize context switches, you might end up hurting response time, right? So these two sometimes might actually be opposite of each other. Sometimes they might be aligned, sometimes they might be opposite. So overall, they're unrelated from each other. So it could go both directions. You might do something that helps response time and throughput. You might do something that helps response time but hurts throughput. You might do something that helps throughput but hurts response time. And you might do something that hurts both of them, hurts throughput and hurts response time. So the bottom line, they're different, and we'll see that. Like in examples, in actual examples, I'll show you that certain decisions might help one over another or might help both. The other metric that you might be interested in supporting is fairness. So far I talked about throughput. You might care about fairness and equality in your system. Like, for example, if you have threads or tasks with same priority, then you might want to be fair among those. So if one of them, for example, gets a certain amount of time on CPU, you want that to be equal over all of them. So you want, if like, I have task A, B, C, all of them have the same priority, and task A gets, let's say, 10 seconds on CPU, I might want task B and C also to get 10 seconds on CPU. I don't want task A to get 10 seconds and task B and C get each one of them 1 second. So that would be unfair, right? So there might be some notion of fairness that you might have. Now, when you talk about fairness, you have to be careful. Do you want fairness over users? Do you want fairness across tasks? Do you want fairness across threads? Do you want fairness across processes? And that differs, right? Because if you're fair, if you want to be fair again across users, you have to consider the fact that some users might have more processes than others. If you want to be fair across processes, you want to take into consideration that some processes might have more threads than others. So how you define fairness is important, and across what you want to be fair is also important in devising a mechanism that ensures that quality of service. So there's somebody's asking, having trouble seeing how context switches is related to response time. Right. So here is an example. Let's say that you have let's see. Let's consider Google search, right? So there, the response time is very important, right? If a search comes, the server has to respond in microseconds. So it's going to go to the database, search for that, and then come back. Now, let's say you have a Google server, you're a Google server, and you're running something else, right? You haven't received anything, and you're running some batch workload. You're maybe there is another task in the data center to be executed, like some simulations or something, and then all of a sudden a search query comes. So if your response time is really important for you, you have to context switch immediately to run that request. And if you don't context switch, if you wait for whatever task that you have to finish and then go and execute the web search query that came, you're going to hurt response time. So this context switch helps with response time because you context switch to the task that needs attention right away, but it will hurt your throughput because of this context switch. You could have waited for this task that was running to finish and then go to the query, and that would have had less context switch, meaning more throughput, but it would have hurt the response time for that query. So when the query comes, you want immediately to context switch to that and get it done. So that's how context switch is related to response time. Hopefully that answered the question. Okay, so I kind of covered this. Now I'm going to stop here. So next on Thursday, we'll start looking at some of the scheduling policies. So we'll talk about first come, first serve, and a bunch of others. So I'm going to stop here. Now, I got another question. Does pipelining in hardware help with response time throughput? Now, generally speaking, pipelining will improve performance if you're talking about hardware. So it improves performance. Now, if you can run your tasks faster, it's generally speaking good for both throughput and response time. But still, you have high-level scheduling decisions to make to use the hardware, right? So pipelining helps with performance, but the downside of pipelining is if you have a really deep pipeline in your hardware. So for those of you who don't know what pipelining in hardware is, you probably should know because you're probably taking the computer architecture course. But anyhow, if you have a deep pipeline, then there is a chance that an exception happens, right? And then you have to throw away, you have to flush your pipeline. So that's the downside. So you get good performance by pipelining because you get each stage of your processing shorter, and now you can do more work. But the downside is if you have exceptions, you might end up flushing the entire pipeline, and that introduces overhead. But generally speaking, what hardware does is generally speaking, in a different scale than what the software does. So in this course, we're going to focus on the software, not the hardware. Okay, so thank you for those of you who attended the lecture. Thank you for those of you who are watching it. Take a good care of yourself. Be safe, and we'll talk to you on Thursday. Bye-bye.